Okay, so we are in Generalized Linear Models with examples in R. We're in Chapter 2, learning about linear models here, and we're on question 2.5. Okay. So we've already seen in the book and in previous questions that our equation for beta hat defined here, is defined here. Okay, we've derived this and we've also been told that. Okay. And so now what we want to show is that our expression here for beta 1 hat, is that its expected value is unbiased. In other words, that the expected value of beta 1 hat is in fact the true beta. Okay, and then we're given a hint here, and we'll come back to that hint at one point when it becomes relevant. Okay, so again, what we want to show is that basically given infinite data, our estimate for beta 1, so beta 1 hat, will equal beta 1. Okay. So so let's go about this. So so here we have our our equation for beta 1 hat, okay, which is just what is given to us. And so we're going to take that y and we're going to substitute in our linear model for y, okay, which is this, right? Our linear model for y is beta, the true beta naught plus beta 1 x plus epsilon. Okay. So again, all we've done is we've taken our expression and substituted y. Okay. And so now, so we have this big, huge multiplication here. So we're just going to multiply each. We're going to multiply beta naught, beta 1x, and epsilon through that term right there, and we get all of this. Okay. And so now we're going to use our hint, and our hint was that this type of sum, where we have the weight minus x minus its mean times any constant a, is 0. Okay. So I guess we're not going to prove that. We're going to take that for granted here. And what we find, so here's our hint, beta naught is a constant, right? And so then that means that this term right here drops out. Okay, so now we're left with the simplified term. Okay, so we have two terms, right? We have the beta 1x times all of that, and then the epsilon times all of that. Okay, well, beta 1, so beta 1 x1 is not a constant, so it does not equal 0, but beta 1 is a constant, and when we have a constant within a summation, we can take it outside of the summation, right? So now that equation right here converts to this, okay, where we just move the beta 1 out. And then we can just separate the fractions, right? So I'm going to take this first part and put it over the common denominator, and then I'll take the second part and put it over its common denominator. Okay, so we have this. Okay. So now let's take the expectation of everything. Okay, so the expectation of beta 1 hat is equal to the expectation of all of this, but by linearity of expectation, we can say it's the expectation of the first part plus the expectation of the second part. Okay? All right. So the second part, it turns out that it drops out, and the reason it drops out is basically because the expected value of epsilon, right? We're defining in a normal linear model, the expected value of epsilon of the error is 0, right? So for any particular observation, we might have an error that's not 0, but we expect the average to be 0, and therefore we expect the sum of the errors to be 0. Okay. So that just leaves us with this term right here. Okay. And now again, beta 1 being a constant, I can take it outside of the expectation. Okay, I'm not proving that, but it's the case. Okay, so now we have that the expectation of beta 1 hat is equal to all of this. So we're almost there. And so what we need to show is that this, the expectation of all of this, equals 1. And it turns out that this expression in here equals 1. It is a constant of 1. And so of course the expectation of a constant is just that constant. Okay. So to show how all of this equals 1, so I take what's inside of the parentheses here. Okay. And, oh, you know what? I've been forgetting to carry my W. Oh, that's not good. But it's okay. So we're just going to ignore that fact right here. It won't make a difference, right? We'll just be carrying an extra W term all the time. So that's fine. But anyway, so imagine that the W isn't here. Okay, so I have X. So I'm just going to expand this part of the fraction. Okay, and this part of the fraction minus the W, of course, by my mistake. We have all of this, okay? And so now I can take the expectation of each of these terms, and so I get the expectation of each individual term. Okay. And then whenever we have a constant, which x bar is, I can take that outside of the summation. So now I have x bars outside of the summation, and 2 is of course a constant, so that comes outside of the, or I'm sorry, outside of the summation. Okay. All right, so we have all of this. Okay. With this term right here, another way that we can write this particular expression, right, is we can just, so I'm summing to, however, I'm summing 1 to n of x bar, but x bar is a constant, so I just have n, or x bar squared is a constant, and so I just have n x bar squareds. Okay? Oops, n x bar squareds. Okay? So now similarly, I can write the sum of the xi's as n times x bar, right? So if I just have n x bars, that's going to equal to the sum of all of the xi's. Okay, so now I can rewrite all of that as this, and I can simplify, right? I have x bar times n times x bar. Well, that's n x bar squared. Okay, and let's see what else. Oh, yep, and so I have it again here. I have x bar, n x bar, so I can just write that as n x bar squared. Well, now here in the denominator, I have 2 n x bar squareds, minus 2, and then plus 1. So I just have minus 1 n x bar squared. And now the numerator and the denominator are equal, and we have 1. Okay.